cursor back over the other screen so that. Oh, you are. Left. Move it off the screen now. We have it.
Okay. Great. All right. So welcome everyone. So today we are pleased to have Patricia Klein coming to us from the University of Minnesota. So Patricia is going to tell us about Gröbner degenerations in algebra and geometry, and I'm very excited about this talk. I hope you are too. So thank you, Patricia.
Thank you, Zach, for the kind introduction, and thank you all for being here. So what we'll talk about today is some rings and modules that break down into pieces with a notion of size. And so what I mean by that precisely is that all of our rings and modules will be graded. And they'll be graded either by the natural numbers or by n to the n or n to the 2n. And so what this means is that we can take our ring and we can break it down into this direct sum. So 0 lives in every degree. And within each degree, we have an abelian group. And there's this rule for multiplication that if I multiply something of, say, degree 5 by something of degree 2, I better land in degree 7. And so some examples of graded rings are the standard graded polynomial ring over C, which means just polynomial ring over C. Every xi has degree 1. And so we can go from this setup to quotient rings that are also graded. So one way we can do that is we take R and we'll quotient by what's called a homogeneous ideal. So a homogeneous ideal means that we have a generating set where each polynomial in the generating set has a well-defined notion of degree. So this polynomial is degree 2 because every term of the sum has degree 2. And this polynomial here is degree 5. So it's fine for the generators to have different degrees, but each generator has to live in just one degree. So then the way that we define a grading is we just say that the degree of the class of F is just the degree of F, if we can write F in a way that's homogeneous. Something else is that we'll be using also an n to the n grading, and this is give degree I the ith standard basis vector. So the degree of x3 would be the vector 0, 0, 1, and then a bunch of zeros until the end. And a non-example is something like if we take R as polynomial ring and we try to quotient by x1 minus x2 squared. This ideal has no homogeneous generating set. And the problem here is that if we looked at the image of x1 in this quotient ring, we would want to give it degree 1. And if we looked at the image of x2 squared, we would want to give it degree 2. But of course, in this ring, x1 and x2 squared are the same. So there isn't a notion of grading that we could apply to a quotient ring like this. Okay, so what do we do once we have a grading? Well, we define the Hilbert series. And so the way that we've set things up, all of these vector space dimensions will be finite. And so we just say, for example, what is the number of, what's the C vector space dimension of the degree A part? Well, it'll be spanned by the monomials in n variables of degree exactly A. And that maybe we learned in a combinatorics class, we can count with this binomial coefficient. And so we take this series that is just what is the degree in each of these finite dimensional pieces, and we form a power series where the coefficient of t to the a is this vector space dimension of the 8th graded piece. One thing to notice is that these binomial coefficients are polynomials in A of degree n-1. And we'll always get this n-1 factorial in the bottom as we move forward to more general settings. And we'll be interested in what the numerator is. So in this case, for a polynomial ring, that numerator is 1, which is a measure of polynomial rings not being very complicated, being good.
Sorry, everyone.
Huh. Uh-oh.
Oh, sorry.
I moved the cursor back over, but I still can't advance.
Now you have to put the phone.
Oh,
Too much technology.
okay. Oh. Great. And this is, so we have a power series, and one way that we can write our power series is as a rational function. So if we write our power series as some polynomial over, we can always pick the denominator, 1 minus t to the d. This is for the standard grading. D is the dimension of my module. Then we get this polynomial that we're very interested in. It carries a lot of information. And the tail end of our power series will always look the same. So this polynomial denoted with k is called the k polynomial. And if we evaluate it at 1, then we get the normalized leading coefficient of the Hilbert series. And so this is called, if we localize the homogeneous maximal ideal, this is the Hilbert-Samuel multiplicity. Or thinking geometrically, this is, if M is a quotient ring, this will be the degree of the variety. And this has a geometric interpretation. So if we intersect enough hyperplanes to get down to finitely many points of intersection, if the hyperplanes are in general position, then this case of M of 1 will be that number of points of intersection. Okay, so in our example of the polynomial ring, we got a 1 up there. And so if we evaluate the polynomial 1 at 1, indeed we get 1. And so this is recovering this information that polynomial rings are not overly complicated.
You might need to click again.
No, sorry. Would you like to be closer? All right, sorry.
Okay. So as we move forward from polynomial rings to quotients of polynomial rings, and quotients of polynomial rings, these are describe all of our affine varieties. One thing that we can do is we can use short exact sequences, which algebraists love all over the place. And so one thing we can do is we can take, for example, this homogeneous polynomial f. We can think about this as arising as the determinant of a 2x2 generic matrix. And multiplication, so including f into r, is an injection, and then certainly quotienting to r mod I is a surjection. So this is one of algebraists' favorite short exact sequences. And what this allows us to do is to say that as an R module, R is isomorphic to R. That multiplication by R gives us a map in one direction. We can divide by R because everything is a multiple of R and we're in a UFD. And so these are the same R module, but with a different grading. So everything in I that's of, say, degree 3 arises as F times something of degree 1. And so we get the count on the degrees of things in I from the count on degrees of things in R, and just it's translated by 2. And so we can describe the Hilbert series of R mod M as the Hilbert series of R minus the Hilbert series of I, because once we restrict to a certain degree, then we have just a short exact sequence of finite dimensional vector spaces. And we know that our dimensions of our vector spaces add across a short exact sequence. So by substituting into our binomial coefficient, we can get that this, and then doing some simplification, we can get that this is the Hilbert series of this quotient ring R mod I. And if we plug in 1 here to this polynomial, so 1 plus t, then we get 2. So this is saying that this is more complicated than a polynomial ring. And it is more complicated, but barely. It's maybe the easiest thing that we could quotient by that wouldn't just give us up to isomorphism, a polynomial ring back again. So one thing that we might notice is that we didn't really care much about F. We just cared about its degree. So we could have chosen any degree 2 polynomial here, and we would have gotten the same answer. And one thing that we might notice is that we could choose an easier polynomial. We could choose, for example, x1 times x2 and represent this same graded module by that information. Okay, so here's another example. So the quotient ring that we want to study is given by xy intersect z. So we could also write this ideal as x times z comma y times z. And geometrically, what is this? Well, it's a plane. It's the xy plane, because either z is 0 and we have no other information, or x and y are both 0, no information about z, so then we live on the z-axis. And we said that the degree was supposed to tell us information about intersection theory. That it was supposed to tell us about points of intersection. And when we're doing intersection theory, we like to be able to perturb things. So we should be able to move our varieties a small amount. And so the number of points of intersection that we get with this variety and any other should really just be determined by the plane. Because by sliding things around, we should be able to move away from the line. And so the information about intersection numbers shouldn't be able to distinguish between this variety and just a plane. And that's the information that we get algebraically through this short exact sequence, where we see that the polynomials of this complicated thing and R mod z, just another polynomial ring, these are both of degree 1. This polynomial over here on the left, this is degree 0, because when I look at the degree of the variety corresponding to this ring, this is just k adjoins z. So this is one-dimensional, so 0 degree polynomial. And so the leading coefficient of this polynomial and that polynomial agree. So I'm just taking something linear and I'm adding a constant term or not. And so this is the algebra reflecting the geometry of intersection numbers only care about the highest dimension variety around. So when we're doing our intersection theory, we want to be able to throw away lines like this. We want to be able to throw away things of the wrong dimension. Oops. Okay. So there's this change of variables that will be currently unmotivated, but will come back to us. A thing that we can do is evaluate the k polynomial at 1 minus t, and then we collect all of the lowest degree terms. In the single graded setting, there will just be one lowest degree term. If we're multi-graded, we'll have multiple variables, then we collect everything of the same total degree. This is called the multi-degree. And it turns out that if you evaluate C and K at 1, you get the same thing. So we can also read off the degree after this change of variables and collection of lowest degree terms. So an example of that is starting from our favorite quotient ring again. We do our change of variables, we get 1 minus t squared. Then we do our change of variables. And the lowest degree term is just this 2t part. So if we evaluate C at 1, we also get 2. So this is our multi-degree. A multi-degree is a polynomial, not an element of n to the n, somewhat confusingly. So when we say multi-degree, we always mean a polynomial that, if we're single graded, recovers the same information as degree. The fact that this is t to the 1 is telling us that the height of this ideal is 1. So the codimension of R mod I, of spec R mod I and spec R is 1. Okay, so we want to understand these multi-degrees. Multi-degrees obey this great associativity formula. So this is telling us that if we take prime ideals that are associated to M, and if they're the right height. So we want to throw away the lines and just look at the planes. And we can split the multi-degree over this integer, this multiplicity, which is the number of times that the prime ideal is associated. So something like R mod x squared, x is associated twice, and R mod x is just associated once. And then the multi-degree of this S mod P. So S mod P is a domain because P is prime. And so we can use these easier evaluations of multi-degrees to put them together and get the one that we were interested in the first place. This multi-degree respects flat degenerations. For us, we'll be interested in partial or total Gröbner degenerations. So this is a strategy we'll have for transitioning from any algebraic variety to an algebraic variety defined by a monomial ideal. And if we do that, or if we get partially down the road towards this monomial ideal, we can retain information about the multi-degree. And this last thing, normalization, just says if I quotient by a variable, then in the standard graded case, what I'm doing is I'm just multiplying by t. Or I'm multiplying by the corresponding monomial if I'm multi-grade. So quotienting by monomials is good. Taking primary decomposition is good. Doing Gröbner degeneration is good. Those all simplify our computations. So here's an example. What is Gröbner degeneration? So as computers became assets to mathematicians, as things became codable, then we wanted ways to be able to ask a computer to decide algorithmically, now that there was this capacity, is this element an element of this ideal? Are these two ideals equal? And so that is how Gröbner bases came about. And what we're looking for is a generating set that gives us a monomial ideal that tells us a lot about our variety. So in our previous example, we could actually replace the degree 2 polynomial we were studying by sort of any degree 2 monomial in sight. But we want to know what is a good choice of monomials to represent our situation. So here's one option. We have this order on the variables where this one's the most important, less important, less important, less important, less important, and so on. And with that ordering, then we'll just, dictionary order things. So choose which letter comes first in the alphabet and then make a phone book. And with that ordering, certainly Z11 is the greatest term of Z11, is the only term. And with that ordering, this anti-diagonal is the most important term of this 3 by 3 minor. So in that case, we'll say that our initial ideal is generated by these two monomials. And the thing that we like about this situation is that the quotient R mod I is spanned by the monomials not in this ideal. And of course, R mod the initial ideal of I is spanned by the monomials not in this ideal. So our measure of size, our Hilbert series, these agree in this case. Here's a different situation. Let's instead start from the bottom and say most important, most important, most important. Then we make. And now that we're getting Z11 and this main diagonal are the most important. And this is not good. So one reason why this is not good is that this main diagonal is already in the ideal generated by Z11. And so if we wanted this to be a monomial ideal that represented our variety, then it would be telling us that our variety is basically like a polynomial ring. Because a polynomial ring mod Z11 is just a polynomial ring again. And we've already decided that the variety we're studying is more complicated. So that means that this is not a good generating set. This will not be a Gröbner basis. Another way to see this problem is here is my second generator minus a copy of my first generator. So I'm just taking off this minor here. Oopsie. Z11 times this 2 minor and leaving the rest of the 3 by 3 minor. This term has a greatest term that is not divisible by Z11. So there's information about the greatest terms of our polynomials that is not captured by this monomial ideal. So it's not big enough. So with that in mind, here are some formal definitions. Term order is a total ordering on the monic monomials of a polynomial ring. 1 is the smallest. And if I multiply something by a monomial, I can't reverse an inequality. A Gröbner basis is a generating set that looks like our first example and not like our second example. So what that means is that if I take just the initial terms of the generators, I should get the whole initial ideal of the ideal. So we shouldn't have situations where I find something in my ideal, but its initial ideal, its initial term is missing. So what do we like? Here's the definition staying up again. What do we like about Gröbner bases? Well, one thing is in terms of these Hilbert functions, like we saw in our first example, as C vector spaces, we get the same spanning set for R mod I and R mod the initial ideal, by which I really mean images of the same elements in R. Obviously, these are different quotients. And from that, we get that the Hilbert series are the same, the K polynomials are the same, and these multi-degrees, which are these things that don't sound like polynomials but are. These agree. So everything about intersections we can capture through Gröbner degeneration. Not everything about them, but degrees. 5 is less directly related to the previous 4, but also very important. So this limit point, this initial ideal, it can be worse than the variety that I started with, but it can't be better. So if the R mod the initial ideal is Cohen-Macaulay, which is good, and we'll talk about why soon, or if it's reduced, by that I mean no non-zero nilpotents, then R mod I also has those good properties. So we can transition to a variety defined by a monomial ideal, which is easier to study typically. And if it's good, then the ring I started with was good. And if it's bad, then I try a different degeneration or some other technique. Okay, so here is the good term order, this anti-diagonal term order again. And let's go ahead and use our multi-degree facts to simplify this computation. So this is the initial ideal with respect to this anti-diagonal term order. And we can take a primary decomposition, which in this case is a prime decomposition, because this ideal is radical. So the way to be in this ideal is to be in all 3 of these ideals. Because if you're in this ideal, then maybe you're a multiple of Z11, or maybe you're a multiple of these, which puts you in all of these 3 ideals. So that tells us by the associativity formula that if we want to compute the multi-degree of R mod I, we can instead compute these 3 multi-degrees here and just add up what we get. And when we compute the multi-degree of just R mod some variables, all this does is multiply the outcome by t each time. So 2 variables gives us a t squared. So we have 3 copies of t squared, which tells us that the multi-degree of this rather complicated looking variety we started with is just 3t squared. If instead we take this n to the n order, where we have that the degrees are these standard basis vectors, then what we get is this polynomial in 3 variables. So this is what a multigraded example looks like. So going through the same simplification. And we'll see things that look like this later. This with this n to the n grading, this is called a Schubert polynomial of the matrix Schubert variety defined by I. So if we want to study these multi-degrees of matrix Schubert varieties, we can go through this degeneration process to get the Schubert polynomials. Okay, so that's why we like initial ideals. So these monomial ideals that come from Gröbner bases. And why do we like Gröbner bases themselves? Well, these are for the computational questions that I mentioned earlier, where we want to know, is F an element of my ideal? Is one ideal contained in another? What's a good generating set for I intersect J? These are all things that, to do them algorithmically, our best friends are Gröbner bases, because there's this long division argument that respects the leading term. And so if I want to know, is F an element of I, then I just do long division on my Gröbner basis in this way that respects the initial ideal. And either I've reduced down to 0, in which case I observe that F is in the ideal. Here it is being a sum of multiples of my generators. Or I get something non-zero, and it can't be that I did it wrong. It can't be that I wrote it wrong. It's deterministic. And so either I see F in the ideal, or I get the result that it's not. And without a Gröbner basis, you don't have that. Because you could say, well, maybe I should have chosen different coefficients for my generating set. Okay, so we like reducing to monomial ideals. I've told you that they're easier, and maybe you didn't believe that and you want to know, well, why are they any easier? And one reason is that if we get a square-free monomial ideal, we can work with simplicial complexes. So there's this correspondence between square-free monomial ideals and simplicial complexes that works by this reverse sort of argument, where a monomial is in my ideal if it is not a face of my simplicial complex. So for example, 2, 3, 4 is a face of my simplicial complex, and it is not in this ideal. 1, 3, 4 is not a face of my simplicial complex, and here it is in my ideal. So this sort of bad behavior that we talked about before, where we had a plane and a line, where we had something of the wrong dimension that we had to throw away, this manifests in my simplicial complex as being not pure. So what does that mean? Well, here I have this maximal face. It's a line segment. It's not contained in any other face. So it's dimension 1. And here I have this other maximal face, not contained in any other face, is what maximal means here by containment. And this is of dimension 2. So in the ideal situation, we get some ideals in our primary decomposition generated by just one element, some generated by 2 elements. So this is a height 1, height 2 situation. So that disconnect is reflected in the simplicial complex of having these maximal faces of different dimensions, which is reflected in the geometry by having things like lines and planes, so maximal parts of different dimensions. Okay, so there are these other complexes, these auxiliary complexes associated to a simplicial complex that can be instructive for us. So one of them is the deletion. These are ways of breaking down simplicial complexes into easier things. So one of them is the deletion, and that is sort of what it sounds like. It's, suppose I want to do the deletion at 5, I just erase 5, and then I also erase anything that needed 5 to survive. So I can't have an edge from 4 to 5 if I don't have 5. The link is a little bit harder. The link is everything that can join up with 5 to make a face. So 3, 4 is in here because 3, 4, 5 is a face of my original complex. 3 is in here because 3, 5 is a face of my original complex. And on the algebra side, what we're doing is, this is a colon ideal, if you like colon ideals. And the easiest way to think about this is we look at 5 and we pull off, think of everything else as a coefficient, we pull off the coefficients. So it's because we have an x5, x2 there, that x2 lands in my ideal. And it's because I have an x1, x5 here, that x1 lands in my ideal. And also we just throw in x5. And for the deletion, what we're doing is we take all of the generators that don't involve x5 at all, and then also we throw in x5. So the complex of the link lives inside of the complex of the deletion. That's a subcomplex. Therefore, we get the opposite containment on ideals, where the ideal of the deletion is contained in the ideal of the link. Okay, so why do we want this? Well, one reason is because we've said that we want our rings to be Cohen-Macaulay, so we can do our intersection theory. And one way that we can find out if our ring is Cohen-Macaulay is to compute the reduced simplicial homology of these links. And I'm not a topologist, so I often find this road difficult. And so exactly once in a paper, I've computed reduced simplicial homology. And there are some related questions where just maybe someone who knew more topology, knew which things were already solved, would be able to make inroads there. So one thing we can do is take the simplicial complex, do some topology, and find out if our ring is good. And another strategy is to do what's called vertex decomposition. So this is take your simplicial complex, break it into link and deletion. If link and deletion have the right dimension and they are themselves vertex decomposable, so it's a recursive definition, then the complex we started with is what's called vertex decomposable, which implies that the ring that we're studying is Cohen-Macaulay. So if we can break things down in this nice way, vertex by vertex, getting rid of them, and get to something easy, so just triangle of an appropriate dimension, then the ring that we were originally looking at is Cohen-Macaulay. So I've said Cohen-Macaulay is good. What do they look like and why are they good? Let's start with actually the non-examples. So here's the non-example we saw before, where we had a plane with a line going through it. So Cohen-Macaulay implies equidimensional. So we can't have these wrong dimensional components that we have to throw away. Another thing, so this is my artistic rendering of two planes intersecting in a point in 4 space. So this is equidimensional. And the problem with it is that we could quotient to get to something that looks like this. So it's not just equidimensionality that's the problem. It is non-equidimensional, or sort of we can get there. So if you can start with your variety and take generic hyperplane sections, you either eventually get down to something that is not equidimensional, where your maximal ideal is embedded, and then you're not Cohen-Macaulay, or you can get down to something of finite length, and that is Cohen-Macaulay. So Cohen-Macaulay is we can take generic hyperplane sections happily without causing any dimension issues and get down to something finite dimensional. So some examples of Cohen-Macaulay rings are polynomial rings, power series rings, complete intersection, determinantal rings. So these are things like we've been looking at, where just define an ideal by minors of a generic matrix. And this is the Hochster-Roberts theorem, rings of invariance of linearly reductive groups. So things that look like this. So for example, affine semigroup rings of a certain type. The ones that look like that. Okay, so I don't really expect you to read this slide, but magic eye at it. These kind of look like the sorts of things that algebraists like to do. So on the algebra side of it, Cohen-Macaulay rings are really great because the homology behaves really well. We like homology, and we can quotient in a nice way, which is the algebraic way to say we're taking a hyperplane section. And this EIR, this is the Hilbert-Samuel multiplicity, which is the degree in our setting. Okay. So sometimes we can get down to monomial ideals, and then maybe we do our vertex decomposition. We find out that our ring is Cohen-Macaulay. We can do our intersection theory relatively easily. We're very happy. Some other times we can't get down to the monomial setting, or if we do get down to the monomial setting, the monomial ideal is worse. And so what are some strategies that we have for that? So one of them, introduced by Knudsen, Miller-Young, is what's called geometric vertex decomposition. And so that tells us to do a vertex decomposition, but there's no simplicial complex around. So we just do the algebra version of what we talked about before. So the ideal of the deletion is formed by everything that does not involve our strongest variable at all. And the ideal of the link is what we get by taking the deletion and adding in these coefficients of our stronger variable. And we just kind of forget these other terms. So this is something that takes us partway to a Gröbner degeneration. So like a simplicial complex throws away one vertex at a time, a geometric vertex decomposition throws away one variable at a time. And so, for example, this is the ideal of 2 by 2 minors in a generic 2 by 3 matrix. And so if we set the lower right-hand corner to be the strongest variable, then what we do is this thing that looks like a vertex decomposition, but we don't necessarily start or end with a monomial ideal. So we end with this stuff over here, which is the ideal of the link, and this stuff over here, which is the ideal playing the role of the deletion. Okay, so in the monomial case, geometric vertex decomposition and vertex decomposition agree. Here is another strategy if we don't have a monomial ideal. This other strategy comes from Gorenstein liaison. And what it is it tells us consider these two isomorphisms of quotient modules. If you get these isomorphisms of quotient modules, you can line up the Hilbert functions. And this is enough to tell you that you have the right initial ideal. So this is a way to either you can do this fully to get to initial ideal, or you can do it sort of one step at a time. So if we have these two isomorphisms, then this is enough to transfer the Cohen-Macaulay property from the variety defined by I to the variety defined by C. So here it is in our same example. And what it is are the isomorphism here is this multiplication by this quotient. And it looks like there's a denominator here, but actually that's an optical illusion, where by adding an appropriate element of n, the x11 will also cancel off, and you'll actually get an honest polynomial on the other side. So this might look kind of hard and complicated, and that's because it is. So finding this quotient isomorphism is typically the hard part. The isomorphism on initial ideals is typically easy like this, where it's just multiplication by your strongest variable. But this is the step that's hard that we'd like to excuse ourselves from. And so here are the types of things that have been studied successfully using some of the types of things. This type of Gorenstein liaison. So it's stuff that are look largely determinantal. So two-sided mixed ladder determinantal ideals, which are minors in a generic matrix in a constricted area, or Pfaffians, symmetric ladder determinantal ideals, these double determinantal varieties that they come from Nakajima quiver varieties. So they come from, they're determinantal things that come from quiver land, or Riesz algebras. And Hartshorne tells us that these isomorphisms are enough to transfer the Cohen-Macaulay property. Okay, so I've told you about these two things, and I've said they're both kind of hard. And the punchline is that they're the same thing. So geometric vertex decomposition is a Gorenstein liaison of a certain type. And so the corollary is that we can excuse ourselves from the hard isomorphism. We don't have to get the isomorphism I mod n to C mod n. So if we understand Gröbner bases of the link and the deletion, then we can, under mild hypotheses, put these back together to get the Gröbner basis that for the thing that we wanted to study at the beginning. So for the rest of the talk, I want to tell you about matrix Schubert varieties and give you an application in that setting. So matrix Schubert varieties were introduced by Fulton. I'll tell you where they come from in a second, but what they are is take your favorite permutation, write down the permutation matrix. So 2143 tells me to put a dot in the second column, then a dot in the first column, then a dot in the fourth column, then a dot in the third column. We shoot out what are called death rays. And then we stand on each of these squares and we look northwest. So here I look northwest, I see 0 dots. So this gives me a rank 0 condition. Here I look northwest and I see 2 dots. This gives me a rank 2 condition. So how do I force my generic matrix to be rank 0? Well, the 1 by 1 minor better vanish. How do I force my generic matrix to be rank 2? Well, the 3 by 3 minor better vanish. And so this is how we're getting these determinantal generators for an ideal. And of course, this is the ideal that we've been studying for a while now. Here is a more complicated picture where it's enough just to stand on these gray things. So the maximally southeast bits of our connected components stand on the square, say how many dots do I see? That's my rank condition. And so these are called the essential generators. If all of our essential boxes form a little scoopy shape here, and there's nothing up there, then that is a one-sided mixed ladder determinantal ideal. that's something that was independently studied in the pure commutative algebra literature. Okay, so here's the formal definition of a matrix Schubert variety. I actually won't read it, but it's there if you want it. So Fulton's theorem is that these ideals somehow are prime, although we're just kind of throwing in a bunch of polynomials. Why would that be prime? But it is. They are all Cohen-Macaulay, which means they are the right types of things to be doing intersection theory with. And the height of this ideal, which we said was the exponent of t in our singly graded multi-degree, is the length of the permutation, so the Coxeter length. And we can read it off the Rota diagram as the number of boxes. Alternating sign matrix varieties are defined in approximately the same way. So now we're allowed some negative ones, and every row and column should sum to 1, and we should alternate 1, -1,1, -1 in our non-zero entries. These matrix Schubert varieties break down into intersections these alternating sign matrix varieties break down into intersections of matrix Schubert varieties. So remember that the associativity formula lets us compute multi-degrees by taking primary decomposition. So this is a setting where we can go from alternating sign matrix varieties to matrix Schubert varieties. This is pretty friendly. But alternating sign matrix varieties are not necessarily Cohen-Macaulay. They're not necessarily even equidimensional. So actually everything that you can describe as northwest rank conditions in a generic matrix, these are all alternating sign matrix varieties. So they're sort of the mother of northwest rank conditions. But as we get more general, we lose good properties. So things that we want to understand are, when are these Cohen-Macaulay? When are they at least equidimensional? So now I'll talk briefly about where these come from. This is a more geometric topological story. So a complete flag is just a chain of n vector spaces. We go up in dimension 1 each time. And so you can build this by taking spans of columns of your favorite invertible matrix. So GLN, we know, acts on the points in complex n space, but also that it acts on the flags. And in fact, it acts transitively. And so by the orbit stabilizer theorem, we can realize the space of flags as GLN mod the stabilizer of our favorite element of the group. And my favorite element is going to be the flag determined by the identity matrix. So the flag determined by the identity matrix, this has stabilizer given by the upper triangular matrices. And so by the orbit stabilizer theorem, we get that the space of flags is GLN mod these upper triangular matrices. So a fact is that GLN can be broken down into lower triangular, possibly times an upper triangular, or sorry, possibly times a permutation matrix times an upper triangular matrix. So maybe we remember this from linear algebra class as an LU decomposition. So these are our LU decompositions, but maybe we have to throw a permutation matrix in the middle if we have something like 0, 1, 1, 0. So which permutation matrix you get determines a decomposition of GLN. And so we have this topology coming from GLN. It's projecting down onto the space of complete flags. And each of these cells, so the image in the complete flag variety of each of these elements of the decomposition, this is called a Schubert cell. And its closure is a Schubert variety. These are not matrix Schubert varieties. These are not affine. So why do we study them? I will not subject you to any more of my drawing. Instead, I will thank Frank Satil for posting such a nice picture on his website. So this is, we might want to ask an enumerative geometry question, like how many lines in complex 4 space intersect any 4 given lines in general position? And so those are the blue lines. The answer is 2. Those are the green lines. And this can actually be rephrased as what is the intersection of 4 Schubert varieties generically translated in the Grassmannian G2-4. So we can use these intersection questions in Schubert variety land to tell us about these really concrete questions in enumerative geometry. They were also very important in commutative algebra. So as we were, I've told you that I love the Cohen-Macaulay property. It's really central in modern commutative algebra. And how did we come to understand it? Well, our first non-trivial examples came from Schubert varieties. So these are important from a purely commutative algebra standpoint also. So this cohomology ring of the flag variety, where we ask how our Schubert varieties intersect, this is actually isomorphic to a quotient of a polynomial ring, which is great for me. Now we're back to commutative rings with unity. And the addition on this ring is just given by the Schubert classes. The multiplication, it turns out, has this really nice basis given by these Schubert polynomials that we've seen before. These Schubert polynomials that were the multi-degrees of matrix Schubert varieties with respect to this n to the n grading. So if we want to understand the multiplication in this ring, it's enough to understand how we multiply two Schubert polynomials and get a sum of other Schubert polynomials. The magical fact is that we don't have to do any cleanup in this ideal that we're quotienting by. We just actually get this equality literally on the nose. These constants are what we want to understand. They're called Schubert structure constants. And so any way that we can get a degeneration, any way that we can get to Schubert polynomials gives us more information about these Schubert structure constants and about multiplication in this cohomology ring. There are also double Schubert polynomials, which is actually what I'll write down today. They have their own cohomological story, and they actually have a double cohomological, a cohomological story. One coming from the affine picture from matrix Schubert varieties, and one coming from honest to goodness Schubert varieties. And the way that this translation goes is we've talked about our projection from general linear group to the space of complete flags. We also have an inclusion, of course, from general linear group to matrix space. So if we take a Schubert variety and then we pull it back along this projection, and then we include it into matrix space, when we take the closure, we get a matrix Schubert variety. So that's how Schubert varieties and matrix Schubert varieties are related and how we can pass between their cohomology. So this is an example of a double Schubert polynomial. How do we write it down? Well, one way is from these combinatorial objects called bumpless pipe dreams, which were in a different language introduced by Lascu and then rediscovered by Lamley and Shimizono as bumpless pipe dreams a few years ago. And the rule is this thing should look like the Rhoda diagram of 2, 1, 4, 3. So it's what we've seen before, where we have our 2, 1, 4, 3. And we've just, instead of having death rays, we've made things bendier. And how do we get these other two? Well, there are these Drude moves. And so a Drude move says, take any rectangle where top left we have a downward facing elbow, down right we have a blank tile, and there are no other elbows in between. Then we can bend either this pipe there, or we can bend this pipe, this pipe there. And that gives us all of the bumpless pipe dreams. It turns out that if we read the indices of the blank tiles, these give us the double Schubert polynomial. So this 1, 1 is this 1, 1. This 3, 3 is that 3, 3. This 1, 1 is this 1, 1. This 2, 1 is that 2, 1, and so on. So the bumpless pipe dreams tell us about the double Schubert polynomial, which gives us information about multiplication in cohomology rings. There is a, due to Knudsen-Miller, an anti-diagonal story, which gets these other objects called pipe dreams and lines them up to anti-diagonal Gröbner degenerations. What was missing was an understanding of these double Schubert polynomials in terms of the bumpless pipe dreams and its own Gröbner story. And so here is a fix. We saw that taking this main diagonal did not give us a Gröbner basis for the ordering that said largest, 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 and so on. But if we zero out this term here, then we do get a Gröbner basis. So this is a Gröbner basis with respect to a diagonal term order. And so here is our initial ideal. Here is the prime decomposition. And when we look at the prime decomposition, we see again 1, 1, 3, 3, 1, 1, 3, 3, 1, 1, 2, 1, 1, 1, 2, 1, and so on. So it is the prime decomposition of the initial ideal that is telling us about our double Schubert polynomials. The theorem is that this is not just a matter of the example being small, but indeed we can always find a diagonal term order so that the irreducible components of the initial variety, counted with scheme theoretic multiplicity, naturally correspond to the bumpless pipe dreams. This was conjectured by Hammaker-Bertunick and Wygant, and there were a couple of special cases in the literature. So this vexillary matrix Schubert variety case is the same as the one-sided ladder determinantal ideal case that was studied by algebraic geometry / combo people and by pure commutative algebraists independently, but actually doing the same thing because Gorenstein liaison in this case and geometric vertex decomposition are the same. So let's see. Here is an example. The result actually also holds for intersections of Schubert determinantal ideals. And I want to put up this example to give an example of what I mean by scheme theoretic multiplicity. So in the bumpless pipe dreams, what we see is that there are two bumpless pipe dreams with a blank square at 1, 1. And in the algebra, in the initial ideal, we're getting this z11 squared. And so that means that the function z11 vanishes to order 2. And so that is giving us our count of 2. So these two tiles are telling us about this squared term. Here is the geometric vertex decomposition. So the geometric vertex decomposition is saying take 3, 3 to be the largest term because we were ordering our variables this way. So if we do a geometric vertex decomposition with respect to z3, 3, these coefficients that we pull off to form the ideal of the link, these come from the blank tiles that we are exposing. You see here for z21 and here for z12. So this drooping procedure in bumpless pipe dreams is geometric vertex decomposition at these southeast variables. And geometric vertex decomposition, again, is an example of Gorenstein liaison. And so it transfers the Cohen-Macaulay property. So what does this get us? Well, one thing is, it's another way to understand Schubert structure constants. So another way to understand these double Schubert polynomials, and then by specializing single Schubert polynomials. Another thing that it gets us is a certain class of Cohen-Macaulay alternating sign matrix varieties. So we said that alternating sign matrix varieties were these mothers of Northwest rank conditions, but that they're not all Cohen-Macaulay. And so this is a way to use degeneration techniques to start studying that. I am over time, so I will just say that you can also do this to get explicit Gröbner bases. Here's a pattern avoidance result. It is understanding the link that is hard and understanding the deletion you hope that you're getting back, an example of something that you've already seen before. I will end by flashing this slide of an example that shows that you can actually get, for different diagonal term orders, different initial ideals. For example, we see the z12 squared here and the z21 squared there. So although Anna and I can get initial ideals, we don't actually get it by understanding a Gröbner basis in a lot of cases. So the best known Gröbner basis result is this pattern avoidance result. And more generally, we sort of have a way to prove the right answer, but we don't know what the right answer is. So I will end there.
Are there any questions for Patricia? I'm curious what you think the sort of next steps are in applying this correspondence you've identified with degeneration.
So we do understand this one instance of Gorenstein liaison in terms of a simplicial complex approach, but being in the same Gorenstein liaison class as a complete intersection is conjectured to be equivalent to arithmetically Cohen-Macaulay. And so there are a lot of other operations. There are a lot of other instances of Gorenstein liaison that we don't have descriptions for, even in the monomial case. So even where you could expect a simplicial complex or a poset complex to be in play, we don't know what the right operation is. So there's some, there's some algebra that's sort of looking for some topology or some combinatorics there.
I'm curious about this construction and those operations. And you could also look at simplicial complexes which are pure and shellable.
Yeah, so shellable is a great condition. So shellable implies Cohen-Macaulay. It is implied by vertex decomposable. And I would love for there to be a Gorenstein liaison analog of shellable. Jenna and I actually had an undergrad working on that a couple of summers ago, and we could not answer that question. But that's a great idea, and I would love to see shellable manifest in the algebra. We mostly just know trivial and non-trivial. To be perfectly honest, I never actually thought about, can we say anything based on how much homology there is, except in one very special case, and that is if the homology is only supported on things that are irrelevant in a geometric sense. So in local cohomology land, which is sort of my home, if I have local cohomology is all finite length, then it means that I'm supported only on, then it means I'm Cohen-Macaulay, except possibly at the maximal ideal. And back in reduced simplicial homology land, we can, so if we're in projective space and the homogeneous maximal ideal is the irrelevant ideal, or if say we're in a product of projective spaces, and so we might have, XY intersect ZW as the irrelevant ideal. Then if the homology is supported only there in a monomial ideal setting, then we do get these virtual Cohen-Macaulay results. So we can say that some homology we want to throw away if we're in a geometric setting, but I don't, except for that very special case, I don't have any interpretation for a sort of homology big or small. Which is not to say there isn't one, just that I'm not a topologist.
Well, if you have any further questions, you can come and ask this Patricia individually after we thank her again.
Thank you.